Okay, in section 10.2, we're going to look at some calculus with parametric equations. Look at the slope of the tangent line, area under the curve, arc length, and surface area. Now remember, the slope of the tangent line is dy dx. Okay, we're still talking about an equation involving x and y here, even though the equations are given parametrically. If we assume that y equals f of t and x equals g of t are differentiable functions of t, then how do you find dy dx? Well, by the chain rule, you could say that dy dt is dy dx times dx dt. So all you have to do is solve this equation for dy dx, you see? As long as dx dt doesn't equal 0, the slope of the tangent line would be dy dt over dx dt. Kind of nice, isn't it? It's easy to remember. You can think of it as the dt's canceling, even though that's not really what's going on. Now, what this says is this. It says basically, if you have a function, if you have a function of x and you want to find the derivative of it, the derivative of this function, let's say, with respect to x, it's the derivative of the function with respect to t, and you divide by dx dt. That's what this says, right? If you have a function here and you want to find the derivative with respect to x, you take the derivative with respect to t and divide by dx dt. So look, so what would the second derivative be? It's the derivative of this thing with respect to x. So what is it? It's going to be the derivative of this thing with respect to t divided by dx dt. That's what this says, see? You may have to stare at this for a while. The derivative of this function with respect to x is the derivative of that function with respect to t. That's what this says. Divided by dx dt. So that's how you'd find the second derivative. So here we go. I'm supposed to give you an example. X equals t squared plus 1 and y equals e to the t minus 1. dy dx would just be dy dt over dx dt, which gives you this. So what would the second derivative be? It's the derivative of this thing with respect to t, and then you divide it by dx dt. See? The second derivative, d squared y dx squared, is the derivative of this thing with respect to t divided by dx dt. So when you take the derivative of this, of dy dx with respect to t, you get this by the quotient rule, and then you divide by dx dt, which is this. It simplifies to this. So that's how it works. Let's talk about area under the curve. This is a little more subtle, I think. Let's suppose y is a function of x for now. I'm using capital F for y as a function of x because little f is used as a function of t, remember? So let's say capital F is y when it's written as a function of x. Then we all know the area under the curve from a to b would be the integral from a to b of f of x dx as long as the function's above the x-axis, right? Okay, well look, if you have a curve that's traced out parametrically, this is important. If the parametric equations are on the interval alpha to beta, x is from a to b, but t is from alpha to beta, you have to assume that f, the x-coordinate at a, I should say the x-coordinate at alpha has to equal a, right? Because you're transversing the curve from left to right. So x at alpha has to equal a, and x at beta, that's just what this is, has to equal b. Let's assume that. Then you can express the area. You can replace y with g of t, because we're assuming y is g of t. And dx, the differential of x, isn't it just dx dt times dt? That's where you get the f prime of t dt. This whole thing is dx, isn't it? Now this is important. You have to assume that you're traversing the curve from left to right. So you have to assume that f prime of t is greater than 0. In other words, as t increases, x increases, right? All right, so here we go. Let's use parametric equations to find the area inside the ellipse given by these parametric equations. First of all, is it an ellipse? Well, this is how you can show that it's an ellipse. If you solve this first one for cosine of t, you get x over 2. And so then if you square both of them, they add up to 1. This is a common trick we've seen before, whenever you have sines and cosines. So you get x over 2 squared plus y squared is 1, which is sure enough, it's an ellipse whose major axis is along the x-axis, right? and it looks kind of like this. Now notice, if you look at it carefully though, this is the subtle part. From 0 to 2 pi, if you were to make a table, for example, when t is 0, you plug in 0, you get 2, 0. It starts off at 2, 0, and it transverses from right to left, you see, or you should say counterclockwise. So we have a problem here. If you were to find the area, I would probably use symmetry and find the area in the first quadrant and multiply by 4. But the problem is it's going the wrong way. I need it to go from left to right so that dx is positive. It's kind of subtle, really. We want dx to be positive. Otherwise, our Riemann sum would be negative, wouldn't it? Okay, so how do you do it? Well, what you could do, what I was talking about is this. If you want to compute the area of this ellipse, I'm going to take the area in the first quadrant and multiply that area by 4. Now, I want to make dx positive, so instead of going from right to left, which would be delta x would be negative, go from left to right. So instead of going from t equals 0 to t equal pi over 2, go from t equal pi over 2 to 0. That is going to make my area positive. Otherwise, you'd end up with a negative. You wouldn't know why. So this is y, and this is dx dt, right? If x is 2 cosine t, so dx dt is negative 2 sine t. You end up with negative 8 times the integral from pi over 2 to 0 of sine squared t. We've done that before. You would, I would probably at this point, you see this negative 8? You can switch the order here. Remember, that's kind of a nice trick to get rid of a negative sign. So I got rid of the negative sign, and I switched the limits of integration. Then I'm going to use the half angle formula for or let's say the reduction formula, we call it. For sine squared is equal to this. You break it up into 2, and you can integrate each one. When you do that integral, you get 2 pi. Pretty sneaky, huh? Let's keep on going. All right, let's take a look at this one. This one's a little trickier. I want to use parametric equations to find the area inside the loop of x equals t squared, y equals t cubed minus 2t. Well, it turns out the graph looks kind of like this. And you could see that by making a table and plotting these points. This is it's kind of a tricky graph. The inside loop is from here to here. You need to figure out what values of t. Starting at this value, what I'm going to probably do is, I think, to find this area, I'm going to look at this area in the first quadrant, multiply it by 2, okay, like we've done before. But notice the direction's wrong. I need to go from left to right. So, but I'm going to first have to figure out where these points are. This one, where's that one? Where does it cross? Where does x and y both equal 0? It turns out when t equals negative square root of 2. Oh, actually, I should say, when is x equal to and y equals 0, right? Where is that point? Well, if t is the square root of 2, then you see x is 2, right here. X coordinate is 2. And if you plug in the negative the square root of 2 here, you can see that you're going to get negative 2 radical 2, and you get positive 2 radical 2, the y coordinate is 0. Anyway, so this is the value of t equal negative square root of 2. Now this one isn't too hard. Where x and y equal 0? I think it's pretty easy to see. At t equals 0 is where the graph crosses the origin here. So the points here are negative. T would be negative radical 2, and this would be t equals 0. You got it? Okay. So anyway, the integral would look like this. I'm going to look at twice the integral. And since I'm traversing it the wrong direction, I need to go from left to right. Instead of going from negative square root of 2 to 0, I'm going to go from 0 to negative square root of 2. And then this is the y. Remember, this is y. Where are we? Here. This is the y, and this would be dx dt, 2t. Anyway, once you got that straight, the rest is pretty easy. You would, I move the 2 out. Then I factored out a negative 1, I believe, and that allowed me to switch these limits of integration. You don't have to do that. It comes out the same. When you integrate, you end up with radical 32. I'm sorry, I should say 32 radical 2 over 15. You can check that. All right, so that's area. Again, it's really important that you that you get the order. Make sure you're transversing it from left to right, otherwise dx becomes negative and then your area will be negative. Arc length. Well, we know what the arc length formula is. The arc length formula back in x and y coordinates is this. So if you replace dy dx, we just got through saying earlier that dy dx is this, right? So this is, I skipped a couple of steps here. When you move this dx dt inside the square root, doesn't it become dx dt quantity squared? That would cancel with this dx dt squared, and you'd pick up a dx dt squared here. So there's a couple of things that we did to get from here to here. We moved this inside the square root and called it squared and multiplied it through. But that's a nice little formula. Look, as long as, if you're talking about the length from x equal a to x equal b, as long as the parametric equations give you f of alpha equals a and f of beta equals b, again, that's so that dx will be positive, then you can write it parametrically like this. Easy to remember, isn't it? Surface area works the same way. If you're talking about the surface area of the solid of revolution, where you're moving around the x-axis, the y, this is actually the x-axis, shouldn't it? This is x-axis, right? X-axis, you have y, right? Anyway, so it looks like this. We just simply would replace, for y, you could replace that parametrically, and you replace these just like we did before. So here's an example. Let's look at this circle, x squared plus y squared equals 4. Let's find the arc length of the circle. We know the answer should be what? 4 pi. Isn't that the arc length of a circle? Isn't that the circumference? Would be 2 pi r, and r is 2. And let's use the formula. So to parameterize it, we could use x equal 2 cosine t, y equals 2 sine t. So dx dt is this, dy dt is that. And now we're going from 0 to 2 pi here. You could use symmetry if you want. But anyway, the answer comes out to be 4 pi. Okay, let's do the last one here. What about the surface area? Oh, with the surface area of a sphere with radius 2. So couldn't you think of it as taking the upper half of the circle, right? Taking the upper half of the circle and revolving it around the x-axis? Okay, so then it would be this. The same parameterization works. The y coordinate is 2 sine t. You put that for y, and like we did before for this is dx dt squared. This is dy dt squared. And notice, this is important. I don't want to go from 0 to 2 pi. I want to go from 0 to pi, because for t, 0 to pi gives you the upper half of the circle, and when you revolve that around the x-axis, it would give you the whole sphere. If you went from 0 to 2 pi, you would actually get twice as much volume as you actually need, because it would count twice, wouldn't it? Anyway, the integral is pretty easy. This inside the square root becomes 2 again. So you get 8 pi times sine t, and when you integrate, you get 16 pi. Sure enough. Alrighty, we'll see you next time. Bye-bye.